Hello and welcome to this episode of Claranet Cybersecurity TV. My name is Ben Thornhill and I'm practice lead here at Claranet Cybersecurity. In this episode, we will be continuing the OWASP Top 10 series and discussing A8, Insecure Deserialization. I'll start with a brief introduction of the OWASP Top 10. I'll then hand over to my colleague Dan, a penetration tester here at Claranet Cybersecurity, who will take you through the rest of the presentation and describe what insecure deserialization means, how these vulnerabilities can be identified, prevented, and remediated. OWASP stands for the Open Web Application Security Project, whose objective is to provide cybersecurity guidance free of charge so that anybody can use the information to improve the security posture of their cyber systems. The top 10 list is what OWASP deemed to be the most critical web application security risks, and they provide this information within an awareness document. This slide shows the OWASP top 10 covered in this series, and today we'll be focusing on A8, Insecure Deserialization. Now over to Dan for the technical detail.
To understand how insecure deserialization vulnerabilities arise, we first need to understand the goal and methods of serialization. Many programming languages use objects in their execution. Typically, these are a way of maintaining many instances of something with particular properties. In this presentation, we'll stick to a user object in our examples. Most applications need to keep track of many users, all of which have their own name, account IDs, and a host of other information. During execution, the instance of a user object will be stored in memory, where operations can be performed on it. For storage and communication, though, we need a way of representing the state of the object in a simple way that is recoverable for more execution later. This is known as serialization. Many serialization formats are easily readable by humans, such as JSON or XML, where you can see simple key and value pairs. Other formats, such as Java's object serialization format, require some manipulation before they can be understood. Deserialization is the process of recovering the original object from some serialized data. A simple example of this being passing a JSON file in JavaScript. Vulnerabilities can be introduced into this pipeline when a user is given access to the serialized data. Depending on the implementation, it may be possible for the user to manipulate the serialized data so that the final object contains different values or becomes a different object entirely. Additionally, unsafe deserialization code may allow an attacker to cause unintended actions during the deserialization process. From an attacker or penetration tester's perspective, where the applications are usually treated as a black box, where we have no knowledge of the implementation on the back end other than what we can observe by interacting with the application, insecure deserialization vulnerabilities can be relatively difficult to spot. Automated tools such as vulnerability scanners have a hard time detecting these vulnerabilities as they often require tailored payloads to have any successful impact. Off-the-shelf exploits tend to require some form of modification to be used. Manual testing efforts tend to be where these vulnerabilities are found. In order to do this, an attacker would typically navigate the application and its functions, attempting to spot any data passed to them which appears to be serialized. Typical signatures that stand out to us are things like base64 beginning with EYJ, as that's typically encoded JSON, or a base64 string beginning with R00, or hexadecimal beginning with ACED0005, as that's typically serialized Java objects. Once serialized data has been found, an attacker will typically attempt to modify the data and observe differences in response behavior. If there are any differences, then these will be explored further in the hope of finding an exploitable vulnerability. If you're fortunate enough to have access to the source code, such as during a code review, the first step to identify potential vulnerabilities is to find the calls to unserialized functions where the data can be traced back to being controlled by the user or other untrusted sources. Where untrusted data is used, you need to check whether the data is verified to have not been tampered with. If the source code for the unserialized function is available, ensure that there are no dangerous function calls within it. And for most applications implementing serialization, there's a strict data type requirement for the final object. If possible, you should ensure that only the correct data types are being passed to the deserialized function to limit the chances of serious manipulation. As with all vulnerabilities, it's important to consider the overall risk posed to the organization rather than simply looking at just the impact alone. Risk is typically described as a combination of impact and probability. For insecure deserialization vulnerabilities, the probability of a vulnerability being present is lower than other vulnerabilities in this series, as it's more rare to allow a user to control serialized data. Where user-controlled serialized data is submitted, however, it's relatively common to find flaws in the deserialization logic. Where there are vulnerabilities present, there is also a slightly lower probability of detection by an attacker than other top 10 vulnerabilities. This is due to a reliance on manual testing and modification of off-the-shelf payloads. Attacks are therefore typically limited to those with at least a basic level of manual testing expertise. If there should ever be a successful insecure deserialization attack, the impact is often extremely high. The best case scenario is that an object is created with parameter values chosen by the attacker, which can often lead to access control issues or a number of other things. More seriously, it's common to see these attacks escalate to remote code execution on the affected host when there are issues in deserialization code itself. Examples of the potential impacts will be shown later in the presentation. While the impact is often high, the probability of exploitation is often relatively low. Depending on a number of factors in the individual implementation, these vulnerabilities typically pose a medium to high risk overall. In this first simple example, we'll be exploring what happens with an object after deserializing if we don't verify its integrity first. We'll be looking at PHP's native serialize and unserialize functions. So this example web application tracks who a user is through a user object. In this simple example, the user object only contains variables for the user's name and role. The user object is serialized and stored in a cookie, which is sent with every request to the application, allowing the server to unserialize the cookie to tell what the user is authorized to do. PHP's serialize function leaves the data in human readable format, which is easily modified. By modifying the string employee in the cookie to admin, the attacker is aiming to be granted administrative rights. When the application receives the user cookie, it fails to verify that the cookie's value has not been modified before deserializing. As far as the application is now concerned, Alice is an administrator and should be presented with all administrative functions, leading to the attacker gaining much more access than they originally were intended to have. In this second example, we'll take a look at a Node.js application, which again tracks its users through a serialized cookie, but is vulnerable to a vulnerability known as CVE 2017-5941. The cookie is deserialized using the Node serialize package of Node.js. All that the example application is going to do is find a user cookie. It will decode it from base 64, and whatever the decoded cookie is, we'll try to unserialize that. And if there is a name parameter of the object returned, it will return welcome and whoever the user is. So it's expecting something like a base 64 encoded version of name : Alice, and if it receives that, then it will simply return welcome Alice. Unfortunately, in the node serialize unserialized function is a vulnerability which we'll discuss. The unserialized function of the node serialize package has the following code snippet, which is vulnerable to attack. We can see that there is a function flag defined, which has the value ndfunc, and then following that, anytime that we see ndfunc at the beginning of a value, everything after that is going to be passed into an eval function. Eval takes some string and attempts to execute it as JavaScript. So basically, any value that starts with ndfunc, everything after that will be executed as JavaScript. Instead of sending name : Alice like we saw in the intended use example previously, if the attacker instead sends the payload that we can see on screen, where the value begins with this ndfunc flag, then the malicious function which we define after it will be executed. This payload specifically will create a child process and will execute a command which connects back to an attacker's machine and will connect a shell to it, giving the attacker a reverse shell which they can use to issue commands to the machine, essentially having full control over it with the security privileges of whichever account it was that invoked the node application. In the bottom screenshots, we can see on the left the example application actually being invoked. We can see on the top right the malicious request from the attacker which has the malicious cookie, and we can see on the bottom right the reverse shell being gained and executing commands successfully. To prevent these sorts of vulnerabilities, deserializing data which is submitted by the user should be avoided when you can. This is obviously the most effective way to eliminate the sort of vulnerabilities that we're talking about. Instead, other architectural patterns are preferred, such as storing the data in trusted locations and providing the user with a unique non-guessable identifier to access the trusted record. Where serialized objects are the preferred option still, then integrity checks should be used to ensure that an attacker hasn't modified the data since it was set. For example, you could cryptographically sign the data prior to passing it to the user and verify that the signature is valid before attempting to deserialize it. Whenever a verification fails, the error should be logged and deserialization abandoned. As deserialization of untrusted data should be considered a risky option, it's advised to run the code in a separate container with low privileges. This limits the impact of any potential breaches should the worst happen. Web application firewalls often struggle to detect exploitation attempts, as the payloads are often completely valid serialized objects and require a deep understanding of the system to know whether they are malicious or not. Some off-the-shelf payloads are more likely to be detected, but relying on OWASP for protection is not considered to be best practice.
Thanks, Dan. That's it for this episode. Please join us for the next instalment in the OWASP Top 10 series, where we'll be looking at A9, using components with known vulnerabilities. Thanks for listening, and goodbye for now.